Gymnasts are athletes that have mastered the sport of gymnastics. However, something you may not realize is that they have also mastered another skill, physics. You can see physics in action when the gymnasts are tumbling. One great example of this is the back tuck. The gymnast has angular momentum when she does a back tuck, and this is because she is moving in a circular path. Angular momentum has a formula, which is angular momentum is equal to the angular velocity multiplied by the moment of inertia. Angular momentum is conserved the same way that linear momentum is conserved in physics. Because the angular momentum is conserved, the gymnast can manipulate her moment of inertia, which would change her angular velocity indirectly. In this photo, when the gymnast is upside down, she tucks her knees closer to her body. This will decrease her moment of inertia. Since angular momentum is conserved, to compensate for the decreased moment of inertia, her angular velocity will increase. This allows the gymnast to turn faster, allowing her to land on her feet. Another aspect of gymnastics that is involved with tumbling is forces, specifically the force of the gymnast. The gymnast gets her force to leap and jump from the forces of her muscles and joints. Her tibio-talar joint, which is the ankle joint, has an internal force of about 11,000 newtons. The talonavicular joint, which is around the top of the foot near the ankle, has an internal force of 8,000 newtons. Additionally, the Achilles joint has an internal force of 7,500 newtons. These forces allow the gymnast to push against the mat to propel her up into the air to do her magnificent flips. Once the gymnast has leaped into the air, she will follow the path of a parabola. Her horizontal velocity stays constant, while her vertical velocity is manipulated by the force of gravity pulling her down to the mat.
Another common gymnastics event is the balance beam. Based on the 4-inch width of the beam alone, it is easy to understand the difficulty and precision that such an event requires. One concept that keeps a gymnast on the beam is their center of mass. When a gymnast is standing straight up on the beam, her center of mass is around the navel but can deviate based on the mass distribution. When the gymnast's center of mass is over the beam, she is fairly stable. However, if her center of mass deviates, she risks succumbing to gravity and falling off the beam. However, when flips or turns are added into the mix, there are ways in which gymnasts need to be able to account for potential mistakes. Oftentimes, you see a gymnast stick out an arm or a leg on the opposite side of their body to ensure that they realign their center of mass so it is over the beam. In this image, you can see how she starts to fall backwards and her center of mass is no longer in line with the beam. So to combat this, she sticks her leg forward in order to regain her balance. Another aspect of the beam that has less to do with the gymnast and more so to do with the beam itself is friction. The beam needs to be made of appropriate materials in order to ensure that the coefficient of kinetic friction is not too high or low between the gymnast's feet or even hands when she does a flip. According to certain sources, some of the first balance beams were made from slippery wood. However, now a leather or suede covering is used to increase the friction between the gymnast and the beam. If the coefficient of kinetic friction is too low, then she poses a safety hazard, and it makes staying on the beam very difficult. However, if there is too much friction, then it could make common turns on the beam very challenging. In this video, you can see as she walks across the beam here, her body is centered over the beam. Then, after the flip, she follows with a jump. When she lands, you can see that her center of mass has fallen slightly to the side, so she uses her opposite arm to regain her balance. Another interesting aspect to note here is the physics behind her succeeding turns. You can see that her arms come in above her head and her foot comes up, thus resulting in an increased speed of her turn. This is because when she draws her arms inward, she is increasing her angular velocity by decreasing the moment of inertia. And then when she wants to stop her turn, she drops her arms back out to the side and puts out her leg, thus decreasing her angular velocity and ultimately bringing her back to a stop. These are some aspects of physics that can be highlighted in gymnastics balance beam.
Another event that you may see watching women's gymnastics is the uneven bars. They are called uneven bars because there are two bars of different heights. The bar heights can be adjusted, but the lower bar is usually set around 5.5 feet, and the high bar set around 8 feet, with the distance between the two bars set around 6 feet. As a gymnast flips around an uneven bar or between two bars, her movement is governed by the laws of motion. A concept in physics that is seen is the moment of inertia, a measure of the distribution of mass around an axis of rotation. When gymnasts are swinging around the uneven bars, their center of mass follows the path of a parabola. When swinging around the uneven bars with a straight body, the distribution of mass is furthest from the transverse axis. The moment of inertia is large, making it harder to spin. This occurs when gymnasts are on a downswing, where gravity provides the turning force, also known as torque. A gymnast will optimize their angular momentum, which is moment of inertia times angular velocity, at the bottom of the swing. When gymnasts tuck their body, there is less resistance to returning motion when the mass is brought closer to the transverse axis and the moment of inertia is relatively small. This occurs on an upswing. Angular velocity is increased by bringing their feet in. In short, in a downswing, gymnasts maximize torque to increase angular momentum, and in upswing, they reduce the negative torque to increase angular velocity.